Okay, and we're live. Good morning, everyone. Good morning, at least for me. So what we're going to cover today is geometry development using DD4hep. So we're going to look at that in a couple of different ways, in two different ways. We're first just going to look at how our geometry is defined in the EPIC repository and in the DD4hep based approach. Where are all those files stored in the EIC shell environment? And then in the second part, we're going to talk about modifying the geometries. What is sort of the steps that are involved there, and what are some best practices, and how to go about that, essentially. As before, you're of course welcome to interrupt me. Anytime you ask me a question is a good time for me to drink some coffee. So that is always a welcome break for me. Any questions? Okay, excellent. So let's get started then. We are going to get started with EIC shell, and in particular start looking at where are those geometries defined of the EPIC detector. So I have my shell here ready, and as before, this is where we kind of ended up in after the tutorial of last week. We have an EIC directory where I have my EIC shell installed, so I can run EIC shell directly from here. But as I mentioned before, I can also set it up so I can run EIC shell from anywhere, which is how I have it set up. So I'm going to go into EIC shell, and since it's a new day and there's a new container on CVMFS, it takes me a second or two longer than normal to start EIC shell, and there we are. So we can tell we're in EIC shell because we have the change in the prompt here, which indicates that that we're in EIC shell. The detector geometries are located in this opt, or under this opt directory structure inside the container. If we look at that, in this opt directory, we have benchmarks, campaigns, detector, and then software and spec environment. It's going to be in this directory, detector, or in other words, in this opt detector directory. If we look in that directory, we'll see there's a number of different detector geometries that are stored there. Let me put them on in one column. So we've got Athena, which is stored for historical reasons to some extent, but also because some people are still doing comparisons between Athena geometry and current geometry for the EPIC detector. We've got Etche and we've got EPIC. Those are actually identical, and Etche is stored under that name because of backwards compatibility reasons. There's a couple of other directories I'll come back to in a minute as well. You'll see that these are all nightly versions. So that means these are built from the latest development on GitHub. Those are just the main branch of the GitHub repository. Once we start having actual geometry releases, for example, for the October production campaign, there will be tagged versions here as well. So we might imagine that we will see EPIC-October 2022, for example, to indicate that that is the version of the geometry that was used for the October campaign. Right now, things are just moving quickly, and that's why this nightly build is a more useful geometry to use. And of course, it will always be the most recent geometry. Thanks to our benchmarks and continuous integration systems, we can also guarantee that this nightly build is actually going to be a stable build that should work, doesn't have any overlaps, no egregious overlaps, and that produces the right response to some extent, right? What we don't guarantee is that it is going to be unchanged. So if we put in versioned geometries here, like an October 2022 version, then that will be not just a working geometry, it will also be a stable geometry that won't change going forward into the future. You'll see there's some other directories here. One is calibrations and one is field maps. if we look in calibrations, you'll see there's some files stored there. Doesn't necessarily matter what they are. Some of them are actually links to other files. Some of them have strange names. The strange names are just a way to make them all uniform in some kind of hash. If we look under field maps, oops, well, that works too. You'll see the same thing here. You'll see an SPhoenix field map, another EIC version 2.0.3 field map. And again, some of these are also pointing to these files with strange names. These are how shall we call them? Artifacts and additional files that the geometries need when we run simulations. So a field map is, of course, something that we will need to run. This materials map is something that is used by the tracking as an approximation of the material budget, so that we can run some steps of the track reconstruction more quickly. There's some other directories here, lib and share, which are just standard Linux file system directories where we store libraries and shared resources. And shared resources are typically, things like those field maps. And then there's a setup script. And that setup script is going to be one of the ways in which we load the geometry, or this is going to be the way that we load the geometry. If we look under the epic nightly directory, you'll see those same kind of things appear. You'll see the lib and share directories and a setup script. If we look under share and under epic, you'll see these calibrations and field maps directories appear as well. So that's where all of that information is stored. However, under this share directory, you'll see additional XML files, and you'll see additional directories, compact, IP6, which contain more detailed geometry information. Now we're going to look into that in a little bit later. We're going to start by just loading this geometry, and we already did that last week, and that's what we're going to do with this setup script. And we're going to use the one that's at the top level here in this opt detector directory, which is going to load the default geometry for this container. So I can do, let me go back to this opt detector directory and just source setup.sh from here. So this has now loaded into the environment of my shell. It has loaded the nightly build of the epic detector, which is the default detector, naturally, for this container. I can also be more explicit, and I could have just done something like source opt detectors epic nightly setup.sh, and that would also load the epic detector. It would load specifically that epic nightly build. And so once there will be other versions of the geometry that you might want to pick, for example, those October 2022 productions, that will be useful to load a version of the geometry that isn't just the latest epic nightly build. Now what happens when we run this setup script? So it does two things essentially. One thing that indicates that it has been run is changing the prompt from the sort of standard jog.xl to nightly. But it also sets some environment variables which will help DD4hep in finding the geometry. So in particular, there's the following environment variables. I'm going to clear my screen here so we can start listing them all on the same screen. There's detector, which includes the name of the detector geometry that's loaded. So in this case, there's going to be epic. There's detector version, which for the nightly build is main, because that's the main branch on GitHub that is being used. If you are running, if you're writing, for example, a benchmark, which is one of the later tutorials, this could be a different name because you might be running on a development branch of the geometry, and so then when you run a geometry, it will actually have this variable detector version point to the name of the branch that you're developing new geometry in. We've got detector config, which is also epic, but this is actually the configuration that we will use of the epic experiment or of the epic detector. Now, what do we mean with the configuration? Well, this is where we specify whether we want the default epic configuration with SciGlass and MRich, or whether we want something that has, for example, PFRich, or a version of epic that has the imaging eCal barrel colorimeter installed. So there's a number of different detector configurations that we support as part of the main epic repository. And this detector config variable includes the one that's currently loaded. And we can change this variable and change which version of the geometry is being used, in particular, again, in those benchmark scripts. All of these three variables are sort of useful for us to know what is being loaded. Ultimately, in DD4hep, the only thing DD4hep uses is a fourth variable, and that's detector path. That just points to the directory that we just looked at, which has all of those XML files. We can look at that again. If we look at the listing of that detector path directory, that's the one that has those entry points, one XML file for each detector configuration. So we have here our epic SciGlass, which is the epic experiment with the SciGlass colorimeter. We have epic imaging, which is the epic experiment with the imaging colorimeter for eCal. We have epic with the DIRC only, epic with the DRich only, tracking systems only, vertex system only, PID only. To some extent, these are to allow faster simulations for those individual systems. But of course, there's also the two major variants on the electromagnetic colorimeter and the barrel. Okay, any questions about these detector variables at this point? And let me pull up the participant list so I can see hands raised and so on. Where's my participants list? There it is. Okay. So in addition to the detector variables, there's also beamline variables. As I mentioned in the past week, we have an epic repository which has the central detector geometry, and we have an IP6 repository which is for the which is for the beamline geometry. That includes the far forward, far backward, and central beamline. Why are these still separate? Well, it's mainly because of historical reasons, going back actually all the way to the yellow report and the start of the DPAP proposal process, when there was still an attempt to consider whether we would be supporting both IP6 or IP8 beamlines. But of course, it's also still useful because it allows for some experiment generality that allows this to be used, or this approach to be used for software efforts also at a potential second detector. Now, in any case, we have this separate geometry repository for the beamline, and that comes with its set of variables, which are beamline, can't spell this morning, beamline config. So that's, there's a little bit of an inconsistency in our naming scheme here. Beamline config corresponds to detector. So that's the name of the repository. And then we've got beamline config version, which corresponds to detector version. So that's the branch within the GitHub repository for IP6 that is being used right now. Again, if you make changes to the geometry of a far forward or far backward detector and automatic jobs in continuous integration run, they'll have this set to a different value depending on the branch of the geometry that is actually being considered. And then there is beamline path. So now we're actually back to the naming scheme that is similar to the detector. And that points to the directory where the beamline elements and the beamline geometry is stored. What you'll notice is that is actually here identical to the epic repository. So identical to what is stored for epic, but it will actually use the files that are in this IP6 directory. And technically we could be using this IP6 directory for beamline path as well. And that is probably something we will switch to in the future for consistency. So to recap, loading the geometry we can do by using the source opt detector setup script, or we add in there or specific detector geometry or detector that we want to load, and then that sets these environment variables. So as a first exercise for today, please just work through that as well. So load the standard epic geometry and verify that indeed it has been set, for example, by looking at this detector variable, and then load another geometry, the Athena geometry, I would say, for example, and verify that indeed the environment variables are different, and that this is pointing to a different directory. And if you have any questions, feel free to unmute and just ask. So when you're done with that and you've loaded this epic geometry and then loaded another geometry, looked at these variables, just give me a thumbs up in the chat so I know, in the participant list, so I know that you're done with that. Okay, good. I see several of you are already done with that. So so let's move on with the next step. So we're gonna look a little bit in a little bit more detail into what is stored in those directories now. So let's go, for example, to this detector path variable, and I'm actually going to be using those environment variables because that allows me to not need to worry about where those files are actually located, and that will be a benefit in many cases because depending on which geometry I've loaded, it might be pointing to a different directory anyway. So using those environment variables is actually going to be a convenient shortcut to not have to worry about which geometry or where the geometry that I'm using is actually located. Now, of course, you do have to know still which geometry is being loaded so that you are sure it's the correct one, it's the one that you intend to work with. But in this case, if I look in this detector path, I see a number of different files. First of all, what you immediately notice is there's a lot of XML files. These are all entry points to the geometry in these different configurations. So there's the ones with EPIC in the imaging ecal mode, EPIC in the SciGlass ecal mode. You also see a list of ECHE geometries. If we actually look at that in a little bit more detail with, we can actually see these are just links to their EPIC counterparts, and they're mostly there for backwards compatibility, and they might actually disappear in some future release of the geometry. So these are just there in some sense temporarily for this summer while we transition from using the name ECHE to the name EPIC, and we allow some time for people to update their scripts from ECHE away to EPIC. So the default configuration that is loaded by default by the setup script is this epic.xml. So it's just the name of the detector.xml. That is typically going to be the detector configuration you'll want to use, unless you are, of course, interested in specific other configurations, unless you're, for example, studying the imaging versus SciGlass ecal, or you're studying MRich versus PFRich, then you would want to make sure that you are aware which configuration that you'll load. We can look at those specific files, and I'm just going to look at the file that is in detector path, and that corresponds with my default detector configuration with XML at the end. So really what this is going to pick out, it's going to pick out, this directory, and then it's going to add to that the default detector configuration, which we looked at earlier, and it's just EPIC. So it's going to look at this epic.xml file. And I'm going to look at that with Les, just to look at some of the major features of that file. As the extension already indicated, it is an XML file, so it looks like XML, or if you're more familiar with, it looks like HTML. So it has these tags, and each tag has a corresponding closing tag that starts with a slash. Tags can have attributes, or they can have content in the middle, and the content in the middle can be another tag as well. So for example, here in this debug tag, there's a sub tag, a child tag that is type, and it has two attributes that each have a value. One of the attributes is the attribute value, but value also has a value that is 0. Okay. What are some of the important lines in this file? And each of those entry point files actually looks fairly similar. Certainly the top looks almost exactly identical, and only at the end of the file are there differences where the specific detectors are included. You'll see a couple of important lines appear in all of those files, and I just want to highlight them because, it might not be clear which ones are the important lines here. But this is an important line where we include definitions, which is essentially or equivalent of the detector parameter table that's uploaded to the menagerie. So that includes the overall detector parameterization, includes, for example, where the D-rich starts and where the D-rich ends, where the ecal barrel starts and how thick it is, how thick the solenoid is, and then how thick the HCal is. All of that is in this definitions file, and those are then the definitions or the parameters that are used by the specific subsystem. So for example, if we define an ecal geometry, we don't hard code in the ecal geometry what its minimum radius is. We just use the value that is defined in this parameterization, this standard parameterization. So if there's ever any changes in the geometry description in the detector parameter table, as there apparently constantly are, the only thing we need to do is essentially update that in our central parameterization, and it will propagate to all systems. That allows some flexibility and it means that we don't have to ask specific subsystems, 7 different subsystems to be updated every time when there's a detector parameter table change happens, but we just need to make that change in one place and it propagates automatically through all of the subsystems. It also means that internally everything remains consistent, because necessarily, for example, the inner radius of the ecal barrel is going to be the same as the outer radius of the MPGD layer that is until right up against that that ecal layer, or it's going to be equal to or the maximum radius of the ecal barrel is going to be equal to the minimum radius of the solenoid. So these are parameters that are at the interface of subsystems, and so that's one of the places where we want to have those defined in one place in a consistent way, rather than allowing inconsistencies to creep in by defining them in different places. So that's our definitions file, and you can see where it is located. It's in this detector path variable directory, and then compact definition. So I'm going to quit out of this and just look at that file to show what's in there. Whether you use the braces or not around the detector environment variable doesn't matter in the shell. Inside these files, we do have to use the braces. So in this definitions file, there are, of course, values defined, definitions defined. Some of them are just for convenience, like pi, mil, or inch. It defines the size of the world volume. It defines detector IDs. Every subsystem in our geometry has a unique number. Again, that's something that we keep track of centrally here to make sure no one picks the same number. So in a subsystem, you would only need to know the name that is associated with the ID that you're supposed to use. It's possible that at some point there will be some changes to these numbers, although we hope not. And if there are some changes to these numbers, they have to be done in a coordinated way. Once we go past about 170 or 200, how many are there now? 213 lines of identifications. Then we actually have the parameters. There's some other convenience parameters here, like the values that correspond to certain ADA ranges. And then there's things like, what's the length of the solenoid in the detector parameter table? What's the R min of the solenoid? What's the thickness of the solenoid? How far is it offset in the Z direction? And then we're starting to rely on that. If we have an R min and a thickness, then we can calculate R max. So we use our previous parameters to determine what R max is, and there will always be consistency between R min, thickness, and R max. So the same thing is done for many of the other, or all of the other subsystems. Bill?
Yeah, Walter, I have a question. So for example, if I have a lattice from the, let's say, the far forward or far backward region, and that's normally stored in ASCII, so what would be the best practice to import those, let's say, columned numbers into the XML format? Do I need to punch the numbers in by hand, or if there is a script we can rely on to convert those?
So that is we don't have a centrally maintained script for that in the collaboration. So this would be, let's see, where are those stored? I think those are actually not in this file, but if I go to IP6, so IP6 has a similar definitions file, and you'll see these are probably the kind of lattice tables that you're talking about, right?
Correct.
Yeah, they might even be exactly this table, right? So you see here, it's actually included in a comment block. So it's not used as data that we read in. What we do is we turn those into blocks of constants that have, rotation angle, center position, X position, length, which is those values in order, right? As you're probably familiar with. So we don't have a way to do that automatically. As it happens, I have a I have an undergraduate student who did write exactly such a script. So we have something that does this for Compton polarimeter work, not even actually on EIC. So I can certainly share that with you, but that's you know, it's a temporary solution. Let's put it that way.
Understood. Thanks, Walter. That's what I was wondering. Yeah, this
Yeah.
example is exactly what I was expecting. Yeah, thanks. Yeah.
Yeah.
This is...
So there have been plans in the past about doing this a little bit more accurate, because we actually inside EIC shell have I forget which accelerator code it is that we have included in there. In EIC shell, you have access to BMAD or to MADX or something. So there are ways in which we can do a little bit of accelerator beam dynamics calculations, which do rely on these tables. And so in particular for far forward and far backward detectors, there might be some opportunities there in the future to do things that really use accelerator beam propagation rather than just the Gen 4 geometry. But that would be a future project. So for now, indeed, I think we would need to take those numbers and translate them into their corresponding numbers for in the XML geometry. Okay. So I've actually now had the chance to point out that there's this other definitions file which governs mainly the beamline and which governs the far forward and far backward detectors. And if we look through here, let's see whether there's anything specific here. Most of this includes just the positions of the magnets. It doesn't actually include many of the detector parameterizations yet for example, the ZDC or DB0. So this is not as well integrated into those definitions and that central parameterization, because there's not as much dependence on things. So if you move the B0 around, it's not going to bump into things as quickly as if you change the radius of a detector in the central detector or a subsystem in the central detector. Okay, let me go back to this starting point, the entry point for the default epic geometry. And in addition to pointing out this definitions file, or of course this IP6 definitions file, which also gets loaded there, let me point out another important file or another type of important files, and that's inclusion of the detector subsystems themselves. So for example, here is where the trackers are included. There's one here where the solenoid is included. So and I'm pointing out the solenoid because yesterday I realized that the tracker wasn't a good example, so we're going to do this with the solenoid today. So we're going to look into a little bit more detail later about how this solenoid file looks like. That describes the materials and the geometry and the magnetic field of the solenoid. Now the solenoid, of course, doesn't have any sensitive elements, so it's not really a detector, but it is a subsystem, and so anything in our DD4hep geometry description is going to be called a detector, whether it's a magnet in the beamline, whether it's a solenoid magnet, or whether it's actually a detector system. That's just the terminology that DD4hep uses. So these are all stored in this detector path, the solenoid, because it's part of the central detector. You'll see also some of these that refer to the beamline path with IP6, where we have the far forward and the far backward detectors, and then the central beam pipe. So those are stored in a different directory tree, and so they use this different environment variable beamline path instead of detector path. So that's just point out that there's different locations where this entry point is then getting its actual detector subsystems from. So let's look at this solenoid file in a little bit more detail now. So if I go and open this solenoid file in detector path /compact/solenoid, you'll see again lots of definitions that are specific to the description of the solenoid. So it has, you know, the thicknesses of all of the different layers of material that are playing a role in the solenoid, of the vacuum vessel, the multi-layer insulation, thermal shields, and so on. Thickness of helium layers, all of that is included in this solenoid. It defines these first as parameters. It again tries to be internally consistent by indicating that, for example, the minimum value of one layer has to be the maximum R value of the previous layer. So there's a consistent set of variables. And then it defines a detector, which is, you know, the solenoid. As I just said, it doesn't have to actually detect anything. It doesn't have to be sensitive. It's a subsystem. It gives it the solenoid ID number, which is defined previously, in which we said had to be unique for every subsystem. It gives it a name, it gives it a type, and this type will be important because we'll come back to that later. That's really what does the work under the hood with this parameterization. It says whether it's inside the tracking volume, which really is a way of defining what the tracking volume is, where we use tracking. So in this case, we don't do tracking all the way through the solenoid. So this is outside the tracking volume. Gives it a position, which we allow to be offset slightly, or, you know, not just slightly. You can offset it a lot, but in this case, it's limited to offsets in Z. It gives it the overall definitions, and then it adds the layers of the solenoid. So it starts with the vacuum vessel, which is aluminum, multi-layer insulation, mylar, and then the copper thermal shield. Gives it an inner radius, an outer radius. No, actually no outer radius. It gives it a thickness, and then a maximum Z extent. So it builds up all of those layers, more layers, more layers. And this is the part where it does the barrel part of this geometry. The solenoid is actually a little bit unique in that it has two end caps and a barrel that is part of the same system. It's probably the only system where all of our end caps, the two end caps and the barrel, are in the same geometry. Now, of course, it's slightly different, slightly special end cap anyway. So we have our barrel that we defined, and we define our positive Z end cap P, where P stands for positive. And then we define our end cap N on the negative Z side. This is a common terminology you'll see in DD4hep, not just in EIC, but in the DD4hep geometry used more broadly in general, is that you have barrel and then end cap P, end cap N. Where end cap P is going to be on the positive side, end cap N is going to be on the negative side. So in this, and then at the end we have another block here, which of course is also unique to the solenoid, where we define the magnetic field that is used for this solenoid. So it's aiming to find this field, download it from this location, store it locally, and use it in simulations. At this point, this is a 1.5 Tesla magnetic field. So we could change this, or you could change this if you wanted to study, for example, a 1.4 or what's the other value, the 2.2 Tesla version. Okay, Stephen.
Does this mean that if you were doing tracking simulations that you would need to include the solenoid then as part of the...
You would need to include the solenoid, yeah. Otherwise, it's not going to use the magnetic field.
Okay, that's good to know. Thank you.
We could, if that is a concern, for example, if you're worried about tracking simulations and that might not want these materials on the outside, maybe due to speed or so, then we can certainly spin this out from the solenoid and put it somewhere else in the tracking system, for example. It's a good point. It's not necessary to tie this to the solenoid. It just I think a lot of things, you end up with a certain structure in some cases for historical reasons. So in the past we had different magnetic systems that we were evaluating, a Helmholtz coil based system, and then a solenoid based system. And so depending on which geometry you picked for the magnet, you also wanted to have a different magnetic field map. Right now, we're pretty clearly going to go with this particular field and geometry for now until we switch over completely all at once. So it's something to think about. Yeah.
I think it would definitely be helpful in terms of speed for simulations, right? Because there's a lot of material.
Yep. So while I'm getting all these questions, of course, I'm taking notes of that for myself so that it can guide us for future development. So let me take a note of that one. Okay. So the important part in this this solenoid file that I wanted to draw your attention to again is this type. So the XML files are only part of the geometry description in DD4hep. They're the parameterization of an underlying geometry plugin. And the underlying geometry plugin is C++ code, which inside the container we actually don't have access to because we only have the compiled version as part of the files that are installed in this opt detector structure. So we're going to come back to that in the second half of the tutorial when we look at the source code that generates, to some extent, this XML file, but also generates these plugins, or that describes those plugins. There is a plugin that is called Epic Solenoid Endcap, and that plugin knows what to do with something that is defined with this many different layers, where each layer has in this case one slice, but could have multiple slices, and it knows how to construct a detector out of that. It knows how to create this for negative end caps or for positive end caps, and then there's an option here that allows us to reflect it from a positive end cap to a negative end cap, which allows us to reuse that one end cap plugin for at least two different things that look very similar. And that's going to be a general best practice for these plugins, is to have them be somewhat general so that they can be used for different detectors, even potentially for definitely for different parameterizations. But they support, for example, a varying number of layers. That isn't something that is hard-coded. They support a varying number of support structures in the case of tracking detectors. They support a varying number of glass block placements or crystal placements for colorimeters. So that parameterization is inside the XML files, can be easily changed. The support for the parameterization is in the plugin and requires a little bit more knowledge of C++ and Gen4 and how it sort of constructs its geometry. That allows people to change the parameterization and even add additional detail here without necessarily having to know the C++ code that underlies all of this. Okay, so I'm gonna put another exercise in the chat here now based on that. So so we've gone through this now for this solenoid detector. We've started from the the top level entry point geometry, epic.xml, and we've identified the solenoid as a subsystem that we wanted to look into in more detail. We've figured out where that gets included, and we've looked at the solenoid.xml endpoint file, and we've looked at some of the parameters that are in there. And then we've identified what is this plugin that is being used, Epic Solenoid Endcap or Epic Solenoid. It doesn't actually have a barrel at the end. Epic Solenoid, period. So I want you to go through that now for one of the detectors that you're interested in, a subsystem that you're particularly interested in, either because you use its outputs or because you're in the detector working group that is associated with it. And go through the same step, look at the file that is included. In some cases, you might have to look at a file that includes then another file, so you might have to go 2 steps deep. And then post the plugin, the geometry plugin, that is this type, in the chat, so I know that you found the geometry plugin type, and I know you're done with this exercise. So I see Stephen picked one that is slightly trickier. I'll come back to that one. Typically, the detector plugin would start with epic underscore, as opposed to DD4hep underscore. The DD4hep underscore plugins have a slightly different role that I'll come back to in a second. So see if you can find another one that starts with epic underscore. Okay, I see that several of you have already located that geometry plugin for the subsystem that you're interested in. What you'll realize is that there's a somewhat standardization of the naming of those detector plugins. So they'll typically start with Epic or IP6. With the Epic repository, I think we currently enforce that. With IP6 we don't, which is why for the ZDC, for example, there's a slight deviation there, and it doesn't start with IP6. If I go back to this, the one that Stephen posted first, DD4hep subdetector assembly, for various reasons for tracking systems, we have to do we have to do some additional work in putting detectors in assemblies that that combine a barrel with two end caps. This is a little bit of an expectation on ACTS and the track reconstruction codes that tracking detectors must come in systems that have a barrel and two end caps. Now, our tracking system doesn't come in that easy of a format. The end caps are pretty much independent from the barrels. There's a different number of them. So we have to play some tricks on DD4hep in our construction of the tracking geometry and put this in some somewhat artificial subdetector assemblies. So essentially, it just adds a logical layer in this structure of the geometry. But it is not something that most of you would have to worry about, because I think essentially Sylvester fixes that every once in a while, and then then no one else needs to touch it until Sylvester needs to touch it again. So which I think is a pretty good approach. So that's what this DD4hep subdetector assembly is for. It's just a logical separation that allows us to treat all of our tracking detectors as this sort of barrel end cap system, even when there's nothing actually in one of the end caps, or there's nothing in the corresponding barrel. Okay, very good. So so now we're going to go take a little bit of a detour to visualization land, and then we're going to come back and pick up that that geometry plugin and use it to make some changes to the geometry in a local copy of the repository. So visualization. Of course, we want to visualize the geometry that we have there, and we'll start with making a visualization of the geometry that's stored inside the EIC shell environment. Now, until now, we've worked in these directories without changing anything, without making any new files. And you'll see if I were to create a new directory here, it's not going to let me, because I'm in a read-only directory as part of the container. So I'm first going to have to navigate to a directory where I can write. For example, in my home directory, I have this EIC directory, which is a directory where I can write files. So what we're going to do is we're going to export our geometry from DD4hep into a format that we can easily visualize, rather than, XML. And what we're going to use for that is a small utility DD web display, which is actually originally intended to open a web browser into the geometry and visualize the geometry that way. Of course, if we're inside the container, then opening a web interface or a web server isn't actually going to be as easy. So what we're going to do is we're going to instead export the geometry. And which geometry are we going to export? Well, we're going to use these same detector environment variables to export the geometry. So this is now going to take our geometry in this location and export it into the root TGO format. The first time I run this, you'll see it will do a couple of things. In particular, if you're familiar with the output of the curl command, you'll see it's actually downloading something here, and ultimately it will hopefully succeed for all of you, and it will have written an output file, detector geometry.root. The detector geometry.root is the geometry, the full geometry of everything that we fed it here, this detector configuration, or epic.xml. It's the full geometry in root TGO format, which we can now open within root. You'll see that as part of loading that geometry, it has also had to download the field maps, and it has also created this field maps and calibrations directory. Because it needs the field maps and it downloads the field maps, we need to be on a node that has access to the internet to be able to do that. This is actually still a small issue that we still need to fix. Technically, there is a field map stored as part of the container, so it really should just use that one. But in this case, that's something that doesn't quite, that we haven't gotten around to fixing yet, but it should normally not need to download this. So if you have any issues, if you're in on a system, for example, that doesn't have internet access, then let me know, and there's a workaround for this. In any case, let's get back to this root file that has been created here. So what we're going to do now is open this in root, but I'm actually not going to use a root installation. I mean, I could use the root that's installed in this container, but I'm not going to do that. I'm going to use a web interface, which is at Argonne National Lab at the location in the chat that I'm posting there. And I'm going to need to stop sharing for that here, so I can share my other window. Share now. Where is it? Here. So I'm going to share this window now. It should be the same size as the terminal window of earlier. And I'm going to navigate and locate that geometry, detector geometry.root file. I'm afraid you're not going to see my pop-up window here, but I'm navigating to the EIC directory and loading that detector geometry.root file. And you'll see it's loaded when it's showing up with its file name here in the root in this text box. And you'll see the file listed on the side. You could do this as well in root, but because of the different systems that we have, it might be difficult to do that. If you're on a system where it's difficult to copy over the files, then you might want to explore doing this in root right now. And I'm just going to copy and paste the commands for that in the chat. But I'm going to continue with the web interface because it's a little bit easier on the live stream, on the recording and Zoom sharing, because it doesn't pop up different windows. So I can go to this geometry, which is in this case called default, and there's a world volume, and you see the entire structure of all the geometry elements in the detector. And we could do things like, well, let's who was it? Kaylee was interested in the Roman pots, so we can go to the forward Roman pot station, right click, and draw the Roman pot station. This will just show that one Roman pot station. We can of course also show the entire detector. So I'm going to go to the world volume, draw, and you can draw default. I'm going to draw all because I wanted to draw everything, and I wanted to make I want the visualization to make an effort at drawing everything. You see it's thinking about it a little bit because this is a fairly large geometry, and it's going to take about 30 seconds before it gets there. It will have a little timer here. And then after 30 seconds, I have my geometry. And those Roman pots are in here too somewhere. I don't know where the Roman pots are, but they're probably somewhere over here.
They're in the gray beam pipe that is behind.
They're in the gray beam pipe. Yeah, I see. Well, let's actually visualize where they are. We can use this second icon at the top, at the bottom left here, to toggle the user interface, and I can turn on clipping in the Y direction. This is essentially going to chop the entire geometry on the horizontal plane so that I can look at what's inside any of those detectors, and I can, all right, let's see, panning. Oh, here's panning. So we can navigate to where our Roman pots are. somewhere. Anyway.
They may not be drawn because there's too many elements there.
So the disadvantage of drawing it this way, and usually I demonstrate this with the central detector, is that there's so many things in our detector that it doesn't, that the visualization actually gives up drawing everything. You'll see it doesn't draw the tracking planes. It doesn't draw the crystals in the colorimeter. Those crystals are there. It just would overwhelm the geometry display if we were to draw them all. And that's why it doesn't draw them. It doesn't draw the mirrors on the rich, for example, even though if I select just the D rich here and I only draw the D rich, it will actually show those mirrors just fine, right? So those geometry elements are there, they're just not always drawn. And this is one of the things that we have to keep in mind, especially when you're using this web interface, is that it is making some decisions for performance reasons to not show them. If you go into the individual detector subsystem, it will actually show them just fine. And I can also go, for example, to the ecal barrel. Where's the ecal barrel? Ecal barrel envelope. I can show the entire ecal barrel. It's in an envelope volume, which makes it a little bit less useful if we do this. I can hide the envelope volume by making it, by showing its daughters and making itself invisible and redrawing it. So I wanted to say checked with daughters and visible should not be checked. If I now draw the ecal barrel, you'll see the barrel ecal with all of its crystals and projective nature. And if we wanted to, we could take another clipping here. In this case, I'm going to take a vertical plane. So in X, that shows the cross section of the ecal barrel. Okay. So we can do this for the entire detector, as we've done in here. We've exported the detector config, which was epic.xml. We could also use a different configuration. We could, for example, export the epic detector with the imaging colorimeter, or we could export the tracker only configuration, which actually wouldn't include all of the additional geometry elements. It would just include the geometry of the tracker, and it's more likely to actually draw this correctly. So as an exercise, identify that a detector configuration that's different from the default one, and export that one to root TGO format, and then open that detector, or open that exported root file in a geometry in a geometry viewer, whether it's the one at Argonne National Lab, this geo viewer, or whether it's in the root interface directly with the commands that I've posted in the chat there.
Yeah, and maybe one extra thing, don't open the TOF only geometry, because the TOF is currently not implemented. So it's going to be very boring.
Yeah.
Walter, so I have
Yeah.
a quick question. What would be the best way for the, let's say, the respective detector? What are the choices? So do you really have to dive into the the XML file to see the options, right?
I mean, generally the names are supposed to be relatively clear. So when it says D-rich only, the intention is that it's just the D ridge and potentially the central beamline, just to give a sort of reference for the z-axis. Does that make sense?
Yeah, it does make sense. Yeah.
And we can add additional configurations there if people are really interested in that. So right now, for example, we have at the top level the EPIC SciGlass and EPIC imaging configurations. I don't think we currently have a full EPIC geometry with the PF ridge. We only have the M ridge in there. So we could do something like that with the PF ridge if was it Stephen is interested in PF ridge simulations. That might be a way to go for that. So
one of my favorite ones is just the inner detector, because that does show all the detail of the tracker in relation to everything else, which is useful for debugging overlaps between those detectors.
okay. So I think we're gonna take a little bit of a break, maybe 5 minutes or so, for everyone to stretch their legs and so. And I'm actually gonna pass the baton to Sylvester, who's gonna do the second half of the tutorial. I unfortunately have to go teach. So I'll Sylvester. I guess I can't pause the recording anymore. But I assume you can pause it.
Okay, so let's see how seamless we can do this without rehearsing. We just had the exercise where we drew some different pieces of the geometry, and I just wanted to double check that people were able to do this. And let me just, do one other example just to get started. So let's do. Also test that my setup works.
Sylvester, a quick question.
Yes, Bill?
So if we, instead of this epic.xml, so then would it work if we put, let's say, the individual detector? That wouldn't work, right? For example.
So you need a top level file. So the reason for that is if you look into the top level file. So let's look at, for example, let's take a simple one, PID only. You can see what happens in here. So let's go down in here. So you see the top level file has a bunch of includes. The first includes is definitions.xml. Definitions.xml includes all of the space allocations for the detector. So that's sort of a top level file that says, hey, this is the total space available for the tracker. This is where the calorimeter is supposed to start, etc. So if you don't load that, of course, none of the detectors will be able to render because they depend on variables in definitions.xml.
I see.
It also includes things like the magnetic fields. It includes things like the different elements and materials and optical materials. Also important. And this is a way that we make sure that we use consistent sets for all the different detectors. So there is some other things that happen in here. So if you want to look at a certain subsystem, either use one of the already available subsystem views, or you can define your own subsystem view. Because you see that all of these are essentially templates where the only thing that is really unique about it is these includes them. So you see for this PID view, we include the fake dirt, the D ridge, the modular ridge, and the central beam pipe. And besides that, you just have the standard things. And we have a way of defining this through a YAML file. It's you know, a little bit tricky to work with. So if someone needs it, we can, you know, provide some one-on-one support here, or you can just take one of these while you're working and modify it to do what you want to do.
Understood. Thanks, Sylvester. Thanks.
Let me share a different window. There we go. So I just exported the inner detector only one just to show a different one. Let me draw this one. And you can see it, you know, it's rendering a subsystem, a subset of our different detectors. And it's rendering much more detailed than you saw before. So you, actually now the tracker planes are rendered to some degree. Some of them are still rendered as layers instead of the actual stave layout. For example, if we were to go to the, say here, the little silicon assembly, you can see that once you start looking at more detail, that's really, you know, you do have a tiled stave layout if we just plot this thing. But by rendering everything together, that's, you know, doing it in this much detail just leads to too many geometry elements for JSRoot to be able to cope with it. And JSRoot, unfortunately, has a hard cutoff at geometry, you know, number of geometry elements, which forces us to either, you know, plot things like we're doing here for the barrel, where we, you know, by default just plot the tube, or it will, you know, cut out different details from the rendering. It will just stop rendering after a certain depth of node. Okay, so let me go back. To my terminal. There we go. Okay, so the next step is that we will, you know, until now we have really been interacting with a read-only version of the geometry. And what we will do now is we will actually work with a local copy of the geometry to mimic actually working on a geometry plugin and editing something. So to start, we will go to whatever our working directory is. And then from within that working directory, let's do git clone. There we go. So I cloned the Epic repository. Let's go in it and let's see what's in there. So you can see here that, you know, this of course looks different than the installed version of the detector we looked at first. So things are quite different, except here for this compact directory. So if you look into the side of the compact directory, you can see these are the actual different components from the detector plugin. So the things that are missing is the top level ones. And the top level ones, however, will be automatically built when you compile the plugin. So let's do the compilation step. So we do cmake -b. We want to call our build directory build -S, or source directory is this directory here. -d cmake _install _prefix. We want to install it in a subdirectory of this directory, which we call install. So let's run the configure step from the EIC shell, and you can see configuration should run successfully.
So Esther, would you mind copy and paste that the compilation into the chat?
Yeah. So let me. You're right. Somehow all my windows closed. There we go. So these are this is here the configuration instruction, and then the second instruction is install. So you just can run this from within the inside of your EIC directory, let's first start with the first command, actually. Sorry for pasting them out of order. You can just start with cloning the repository. So you go to your epic directory, or your EIC directory, which in my case is called tutorial. Then within there, you execute a git clone. Then you go inside of the repository you cloned. And from inside that repository, we execute the CMake CMake line, which somehow I don't remember anymore. So you do CMake minus B build. So if you look in the directory here, there's now a build subdirectory. So the CMake minus B build says build will be my build directory. This directory is my source directory. And install will be my install directory. Install isn't here in the directories yet because I haven't actually run install yet. So then I run the second line that I had pasted in the chat. Oh, actually, I made apparently a typo in here.
Yeah, so the install, yeah, there we go.
Yeah, so you see there is a minus J number. So after that, that means number of jobs. So number of parallel GCCs that you execute. I'm on a system with a lot of cores. So let me just, take 16 here, but just put your number of cores in your system after the J. That will make things go faster because else it goes one by one and it takes a while. And this command is CMake minus dash build. So you tell it, hey, compile whatever is in build. Use 16 cores for it. Then you have a dash and a space after the dash. And then you tell CMake, and after all of this, execute install. This is equivalent to doing make minus J16 and then make install, which you could do. You could just go into the build directory and execute manually. This is sort of a more modern way of doing this, which allows CMake to specify different build systems. So it works with other systems besides Make. So for example, you could use Ninja as a build system, which has some advantages for bigger projects. And it's less typing, which I like. So there we go. I'm on a pretty big computer, so this built really quickly, but depending on how you're running it, if I were running this on my personal laptop, which is one of those ARM MacBooks, it actually takes a while because it needs to run this through emulation. So okay, so now we built everything, and you can see now there's an install directory here as well, and that has all the installed components in it. So you see, similar to what we had before, there is a setup.sh, and there is a share directory. So if I look at install share, it has Epic in it. And Epic has, again, as before, all of those different components in it. So you have all of the rendered XML files from before are installed. So if you want to use the detector from here, there is really a two-step process. We need to still do the source. You don't have to do this again if you're still working in the same session, but you still have to source op detector setup.sh. So what this will do is it will load the detector, and it will load the beamline. Of course, we only now cloned the detector repository, not the beamline repository, and we only compiled the detector repository. So we still need to set the relevant variables for the beamline. But on top of this, we now source the install setup.sh, and that will set everything up correctly for it to use the files that are installed. You see that it warns here that IP6 is not loaded. That makes sense. We did not build IP6 ourselves. But if we look at our environment, you can see that the relevant environment variables for the beamline configuration are actually set. So is this working for everyone?
No. Sylvester, I followed your steps, but it's complaining. It says that there is a configuration that is incomplete.
During the CMake step?
Yeah. So what did I
Okay.
do? I did the git clone, and then I did the CMake -b build, and then yeah, there it goes wrong. Sorry, in the CMake -b.
Okay, so did you go inside of the directory you cloned?
Yes, I mean Epic as you. Like I made the tutorial directory as you and went into Epic.
Yeah, and you did CMake -b build -s period.
I did, and this okay.
So this says
and-
build directory is built and source directory is the current directory, because you
so
can
there
actually
is-
execute.
So when I do this, it says configuring incomplete, errors occurred.
Okay, and you're
I
doing
have
this
a-
from the image? So from
yes,
the EIC shell?
Oh, that's the problem I did. Probably that's wrong. Wait.
Yeah, Charlotte, would you like to copy like what Sylvester is having? Would you mind copy a few lines of your, let's say, just terminal where the complaining error and a
Wait,
few
let me first try.
So you do need to compile from EIC shell because you need to have a working install for DD4hep and ACTS for this to compile.
Okay, let me try all this again. Thank you.
Oh, no problem. Yeah, and else indeed we can, an error message would be helpful to help identify what's wrong.
Yeah.
So Sylvester, I have a quick question. So what's the incentive, or why do we source the default /orb/ detector, basically the default setup file? So why are we doing that if we want to source the local build?
That is, well, it's something that is still something we're optimizing a little bit, because I'm not super happy with having to do this. What it does is it sets the relevant variables for IP6. So we really have a two-component geometry. We have, for historical reasons, the beamline living in the IP6 repository and the detector living in the Epic repository. So we need to tell, let's just open one of these files, okay? They'll probably become more clear. So let's look at epic.xml, for example. You see here, there's the variable beamline path, which has the components for the far forwards in it. So we need to tell it where those live. So unless you also install those locally yourself, which you could do, you still need to set those variables. And right now, if you look here, if I look at my environment, after running this, the op detector setup.sh, it sets those to be loaded from the container. So that's why it's still there, because everything related to the detector is set to my tutorial directory now.
Yeah, that makes sense. And yeah, that what you said correlates to the warning that we get after sourcing the local build. Says warning, IP6 not loaded. And
yes,
I see
that's
yes.
Yeah, you could in principle load IP6 together with this. It's probably something that will slightly change in the future, although you will keep having to source this. And Bill, if you remember, in the past, we used to have a system where we had to manually set symlinks, which I think was more clunky than this, or more error prone for sure.
This is good. I just have one more question, Sylvester. So if we want to, let's say, source a nightly build and or other build, so we don't have to source the default setup in order to set everything right. Is that correct? For example, the default build in the, let's say, the nightly or Athena or HA or other basically default build in the /orb/detector.
You don't have to do it, but then you have to provide your own IP6.
I see. Okay, understood. Okay.
If you do exactly the same thing for IP6 as we did for Epic.
Well, yeah, I understand. It was just not very clear to me from Walter's earlier setup. Then now I understand. Okay. So
So if you want to if you want to work on the far forward, for example, and still check if it interferes with a detector, this is something you would do. You would work from the IP6 repo directly. You would build both and source the setup.sh of both.
Understood. Okay, thank you. Thank you. Yeah, that makes complete sense.
Okay, Charlotte, did you
all set? Thank you very much.
All set? Wonderful.
Yeah, thank you.
Any other issues?
Yeah, hello, Sylvester, can you hear me?
Barely, but yeah.
Barely. Maybe I'll type my question in again then. So when it gives a warning that IP6 is not loaded, is it just saying that it's not been given like a custom location or?
Yes.
Yeah. Okay. All right.
It means it doesn't detect that. So if you were to
so it still has the default IP6 location because once
exactly.
Yeah.
So in principle, you could put you could actually link the IP6 from Epic, and then it would detect that it's there, and it would also add the IP6 variables directly into setup.sh.
Okay.
I think we need to make this setup.sh talk a little bit more and be a little more clear, because right now it shouldn't warrant the most common workflow, which is this one, which is a little confusing.
Right.
Okay, so if everyone is up to speed now, then we can now actually export the geometry from our local install. So to do that, we can again run DD4hep display, and we will use the following directories. So we have our detector path, which is now set to some local path wherever you're working. And you will use some detector configuration. Detector configuration is Epic. So if we then run DD4hep display, so we're running over a custom install here, which is under detector path. And we use our detector config.xml, which is set to Epic. Then this will run the exact same export as we did before, but it will do it on the local version of the detector. And you can see as before, it has to download the calibration files and the field map, I believe. Okay, so here is the next exercise. How can I copy this easily? Here is the next exercise. So the first part is ensure that you have a local copy of the geometry repository and you can compile and install in a local directory. I think we pretty much covered that already. Then second one, verify that after sourcing setup.sh, detector path points to the correct local install directory. And then the third part is verify indeed that this DD4hep display actually works. DD web display is another executable we should probably rename, because we initially used it as exactly that, a web display, where we then added the export function, but now we're mostly using it for export. So it could probably have a better name, DD geo export or something.
So Sylvester, the rendering constraints, that also applies on the local machine, right? If you go with the root plot route, that would be the same.
It will not necessarily be the same, but there will be similar limits somewhere, yes, in the amount of nodes that it will allow.
Understood.
I think JS root is a little bit more aggressive, and which is unfortunate, because I don't think from on a modern machine the limit actually matters that much. Like WebGL rendering is very fast on modern laptops or phones. I think actually hardware-wise we could do with more. And one of the things we are looking into, in the next stage, is maybe use a different web renderer for this. There is this web display package called Phoenix that they use at LHC, which is based on modern web applications, which actually looks really nice for web display to also have an event display that is purely in the browser. And that sidesteps some of these problems that we have with JS root. But the JS root part is nice because really it comes for free with root. So we just export the TGO tree that we give to DD4hep, and now we can put it in the browser, which is very powerful. And in principle, this could also be used to make a web-based event display, as the structures that you would use for something like TE are also supported in JS root. So you could make a TE style web display this way. Okay, is everyone up to speed? Please let me know if there's any issues you're running into. The next step is that we're going to look inside of a detector plugin, and at a very sort of broad level, we're going to look what it takes to make a modification to one of the detector plugins. So in principle, the workflow would be you make a modification to a parameterization, so which is to the C++ plugin, or to an XML file. You commit them in a branch in a local repository, and then you submit a pull request on GitHub to get them included in the main branch. So to really understand how to do that, we should look inside of one of the detector plugins. And for this one, we can go into the Epic vertex barrel, for example, which uses the barrel tracker with frame plugin. And I do have to warn that this is one of the more complicated plugins, because it's essentially a plugin that is written in an extremely generic way. What do I mean by that? It actually allows you to set arbitrary structures for supports. It allows you to put in a frame for the detector itself, which is a stave style detector. And then it allows you to arbitrarily put different layers within the detector staves to really get to extremely flexible geometry plugin. So I'm not going to go into a ton of detail about through everything we're doing here, because this one is very complicated and actually something that I see us changing in the future, in that as our detector becomes more concrete, we're probably better served with having a detector plugin that is a bit more specifically tied to the detector and does some things automatically, like builds rather than being able to build arbitrary supports, just build the right support based on how the detector is set up. And I foresee that we'll have a lot of tasks like that in the future. The more we make very specific choices or have the engineering down for certain detectors, we don't really need the generic aspect anymore, but we need something that's a little bit simpler to understand. One question: did Wouter go through the file at all, or any of the plugin files at all?
Like the XML or
the C++ source code? Did he go through that already?
No,
He has not?
No.
Okay, great. Then actually, let me take one step back here. Let me go into the compact directory and look at the vertex tracker. A lot of the newer files are put in a directory structure that is a bit more tiered. So you can see here for ecal, we have a lot of ecals, and we're trying to get a bit away from having a compact file that just has a big dump of different files in it. So we have here a tracker directory that has the different tracker components in them. And the one we want to look at is the vertex tracker. And this file, I think Wouter has already gone over. Let me close this window. There we go. You can see that it starts with a set of constants that are used to build the detector, and then you have the actual detector plugins they're made. And the type here that is set is the epic vertex barrel. So how is this linked to C++ code? So this is really the link to the C++ code. So if I go now to the source directory, and I do grep you can see that this is defined in this file called barrel tracker with frame. This is the only place where the word epic vertex barrel occurs. So let's go into the epic vertex. Let's go into barrel tracker with frame. And all the way to the bottom. And you can see here at the bottom, there is a lot of preprocessor macros that do one thing. They link a name of a detector, in this case here, epic vertex barrel. They link it to a C++ function that actually creates this detector. So here we see that epic vertex barrel, what it does is it calls create barrel tracker with frame. You can see that for this particular one, we actually use the same very versatile plugin for all of these detectors, because really this plugin is versatile enough that we can use it for so many different detector systems. That comes at a cost of complexity, of course. What you also see is that we have for every single one of these, we also, in case we're building this in the compatibility mode that Wouter talked about, we also built a version that's called @_, and that is just to deal with XML files that hard link still to the old names, which is something that I think will migrate away from very soon. But we're trying to be gentle with these changes and allow for backward compatibility. So we don't break people's code overnight when making drastic changes, as in changing the name of everything. Okay, so let's look at what this create barrel tracker with frame does. So, and this example is Akio, did you are you able to find the source directory? So it's in the, if you go into the repository you cloned, it is in the source directory. So let me just exit here for a second. You can see here, this is my EIC directory, which I called tutorial. Then you have Epic, and then you have source. And that has all of the plugins in it. So you see here that we have a function here that returns a reference to a detector. It takes a detector description, which is really the big tree of the geometries that we're building. It takes a XML file, which is the XML info that we're passing it. And that is really whatever is put within the detector tags for this detector that is passed into this function. So the function has access to everything we give it in the detector tags, as well as a handle to the sensitive detector, which we can then use to actually make part of the detector sensitive. And besides that, there's a lot of things happening in this code for getting, for example, the XML file here, so which we call xdet. Here we're using the description that has already been built to get some material. So here we get air out of the description, because our description defines what air is in the geometry. And then there's a whole bunch of module construction. And I'm not going to go into a lot of detail here, except that things are really very similar to how you would do the construction in Géant itself. And a lot of the names of detectors are roughly the same names as they are in Géant, but without the G4 prefix. So what else does this do? It does some boilerplate code to work with ACTS tracking. That is something that will disappear very soon. With the new ACTS version, this is luckily not necessary anymore. It then defines the detector as an assembly, meaning we're assembling different components together. The first components we're looping over. So here you see we're looping over X detector. Over the support field is we're going over each of the things that are supports, and then based on what support is given, we construct this. And this is really something that is very generic in that we're able to really get arbitrary shapes such as cones, etc., built here. So that's something it's a little complicated, and I would not suggest to spend too much time looking at it. The next part builds the actual modules. So in the XML file, we define a module, which is a stave. And then after that, we build the stave in different layers. So here is the piece of code that actually builds or defines what a stave looks like. And it places all of the different components to a stave. A stave has a optional child, which is called a frame. And a frame is one of those triangular shapes that you saw when I showed the silicon tracker, which is the triangular sort of service and support, which, right now we have a triangular piece of carbon fiber that supports the stave that sits at the back. Not for the vertex tracker itself, of course. So then there is a whole lot of code that then loops over all the module components. So it takes the XML file for the module, and it loops over all the module components and then places each of those components. So, this could be silicon and some aluminum, some carbon fiber, etc., depending on how the detector really should be built. And then when we get through a component that's labeled sensitive, we make it sensitive, and we give it a volume ID based on the sensor number that this should be. And then we built all the layers. So we loop over all of the layer fields in the XML file, and we construct them based on extra things that are possible within. For example, if we have a module, we say the module needs to be repeated this many times. We start at a certain phi position. We have an optional tilt of the module, such that you can tell them a little bit overlapping. There's a lot of different options here, and it's sort of beyond the scope of what we're doing today to go through this in detail. And then finally, we attach everything to the initial assembly, and we add the assembly to the detector description, and then we're done. We've built the sensitive detector, we return it. So there's a lot of things happening here, and yeah, really, typically you will not have to write any of these from scratch anymore, because we do have good examples for every single subsystem available. And except for maybe some rare cases, we'll start from these different ones that we already have available, to then specify it, to make it more specific or maybe more detailed for a specific detector system. One of the things that I do want to show is, we can edit this, and we can maybe add a print statement to this and show that this print statement actually works. And let's look at an example of something that already has a print statement. The file loader is one of the plugins that has a print statement. So in order to do a print statement, we include printout, which uses the DD4hep print system. And then we can call the printout function to print with any of the modalities, such as, for example, debug or info, etc., a message. So if we go to our barrel tracker with frame, let's add a print message. And let's print the detector name. So this is my name. And we get from the XML file the name field. So we can add printout info. This is my name, xdetector.namestring, which is the same as what we're calling here. And to make this work, of course, we need to make sure we actually include the printout functionality from DD4hep, which is already included here. So great. So after adding this, we can go back into this directory and we can run our compilation again, which, just as a reminder, is this command. We say we want to build the build directory again and run the install again to make sure everything is installed. You can see that I made a mistake. Oh, I see. Yeah. Bear with me. This is kind of unscripted, so I'm not. let me look at another use case of this one. So let's look back at the file loader, and I'm sure we can figure out what we did wrong here. I see.
Include the printout.h?
Yeah, so the problem is I didn't look at the function signature of printout. So what printout takes is it takes a modality, it takes a tag of who is the caller, and then it has a message. So it takes 3 arguments, not 2 arguments, and I only gave it 2. There we go.
Yeah, Sylvester. Oh.
Yes? Yes, Bill? There we go. So this time it worked. And now if we run, for example, DD4hep display again from this directory, we should see when it actually passes through the printout statement. Which I didn't here. So let's print it as a warning instead. And my apologies for the for the trial and error. It's relatively last minute that I knew I had to give this tutorial.
So recompilation is only needed when you change the plugins, right? If you change the
That is correct. That is correct. So if you want to work on a plugin, which in a lot of cases, the files that you really have to edit are, for example, the main level of definitions. So definitions is made to be edited. It has really everything that we need in it. So for example, it has the different solenoid options in it. This one is commented out. So here you have the solenoid length, solenoid min radius, thickness, etc. It has the tracking regions set. Where does the tracker start? Where does it stop? And a lot of these things then influence where the next volumes are located. For example, the Z-min of the forward PID region is the Z-max if the forward tracking region. So PID starts where tracking stops. And this really allows us to subdivide the detector in different volumes, which match what's in the menagerie. And then within these volumes, we can then place our detectors or maybe play around with different detector options. So this is a very important file to keep in mind, because a lot of times when someone wonders, hey, why does this detector start at this particular radius? Then the answer is, oh yes, that's how the volumes are allocated within the definitions. So, but for the cases that you need to work on the C++ plugins, then you need to recompile the plugins and reinstall and make sure they're loaded. And you can see, this time when I kicked up the log level to warning, it actually printed the log level. And that's because apparently, currently in our setup, we're only printing warnings and errors, and we're not printing info messages to make things a little more quiet. So you can see here, barrel tracker with frame was called a total of 5 times the constructor. It was called for the vertex barrel, for the Sagitta layers, for the outer silicon barrel, and for the inner MPGD and the outer MPGD barrel. So you see, this is really a very versatile plugin that was used for some very different detectors. Let me show again how I did this print. So So I print warning. I say, hey, the warning comes from barrel tracker with frame. And then I print the name of the detector from the XML file. And the format is probably actually not needed here. Let's see if if this works without this. If I just put a plus sign here. Yep, it does. So you can see here printout, warning. We wanted always to warn. I'm from barrel tracker with frame, and I print out, this is my name, and then the name is the name of the detector. And we can call this because we get the XML file here with all the elements, which is what's called E for elements. Then X detector, the XML descriptor we get here, and then we ask it what is the name string that was given.
Yeah, Sylvester, could you copy and paste this line in the chat? Thanks.
Yeah, sure. Let me also give you the other line that needs to go with it, which I think for this file wasn't necessary, but in general, this is the header that actually in DD4hep that actually defines printout. So in case you get a compilation error of, hey, I don't know what printout is, this is where it comes from. So you do this, you then run the compilation command again. And then when you do anything really with the geometry, so here I'm calling DD web display, but also when you're running, also from the printout, remove the curly braces. Those are for format, so those are not needed, these here. So really it should look more like this. There we go. Okay, do you have any questions about this? Are people able to edit and recompile their plugins and then verify that the plugins are actually loaded? I don't hear anything, so I'm assuming people are still doing this. So one thing with the recompilation command to keep in mind is that there is a space. So install is not a flag. It's a second command that you pass. So the dash says this is the end of the primary command, and then you add a second command, which is install. You can also do this in multiple lines, but why do it in multiple lines where you can do it in one? There's of course a lot of there's a lot of little details to look into when it comes to how these geometries are really built. You can see that we are here, for example, we're loading. This is from the Solenoid geo.cpp file, which is a little bit shorter and therefore a little bit easier to follow. You can see that the Solenoid geo, if you remember from when Wouter showed it, it consists of different slices. And you can see that for each of those slices, what we do is we get the XML descriptor of that particular slice. Then from the total detector description, we look up within the materials the material name that was given in that slice. That's your map here. And then we build a tube volume out of this material. So we're building a tube with a certain size, and then we make a volume here that is out of the tube that uses this particular material and that uses the name of the detector. Hello? I think I lost my connection.
No,
How long
hear
have I
you.
been gone? Oh, you heard me? Okay,
Yeah.
because it stopped sharing and it was loading. Okay, great. I think I covered pretty much everything that Wouter asked me to cover. Do you have any additional questions? Or anything else you need help with, Stephen?
Hi, so I was wondering, so when you change the geometry, if you were to move something to a different radius or make it thicker or something like that, presumably that changes the material map.
That is a very good question. And this is one of the things that is currently a little bit annoying about how the workflow with ACTS works. So suppose you, I don't know, add a 5 centimeter thick layer of aluminum in the center of your, inside of your tracker. That of course impacts your tracker, right? And to properly track through that, you need to have that in your material map. So the way that the material map is created right now is that a person, and that's mostly been Shuji who's done this, does a Giantino scan of the detector, and then based on that comes up with a binning for the material map, or saying, these materials need to be mapped to these volumes or these surfaces, and then we can do it with this granularity and still reproduce the Giantino scan well. And then based on that, she does the actual scanning to make the map, which we then download. That workflow is a little bit convoluted. So assuming that we don't change any of the main properties of the detector, and there I mean the order of the different detector planes or detector systems, we just add some material somewhere. We can in principle reuse the binning, and we just need to do a different scan. This is something we're in the work of optimizing, because ACTS in the last week actually put out an improvement to the procedure that speeds it up by a factor of 20, I believe. So it used to take many hours, and now it can be done in minutes, which is of course a huge improvement. But it is still a little bit of a manual procedure, because you need to manually specify exactly what surfaces are important to map things to. There are some ways of actually doing that in the XML code directly, so you don't need the manual intervention for the map. And that's something that we're working on right now to get fully in place. But you can see, for example, if we go into the tracker and say we go to the say the silicon barrel. Then within the different layers, let's see, this one has it already or not yet. This one actually doesn't have it yet. Yeah, there we go. So for example, that's the old vertex tracker. Yeah, here, for example, you see the layer material line. That is something that's ACTS specific and has to do with the ACTS plugin. So here we say that the material needs to be mapped on the inner surface, which is the one that we first passed through. Then we give it a binning in phi and z. And for the first variable, which is phi, we give it the number of staves, meaning that we expect a symmetric material based around the number of staves, which makes sense. And then in Z, we use 100 bins. So that's the default. And in principle, that's something that during the procedure people can change. There's more information on the ACTS website about how exactly this procedure works. In practice, unless we make very drastic changes, the material map will actually keep working if we just slightly move some detectors around a little bit. It doesn't really matter if we map it on a surface that is, shifted by 1 centimeter or something like that. But if you were to add a substantial amount of material inside of your tracker, of course, things could change. The error of using the wrong material map is that your tracking resolution will come out worse than it should be, because the X propagator isn't aware of the extra material that the particle would go through. But it wouldn't immediately break things necessarily. It would just not run at the best performance for the algorithm.
I see. That's helpful. Thank you.
And really, Shuji is the person who's the expert in this, because she's been responsible for this for a long time, and she's working right now with detailed material map for the newest tracker version. Any other questions? No, we have still a couple of minutes before the general meeting. So you load the file. Let's you don't need anything special for this to load the file. So let me share a screen here. Where is the button? Do you see my screen?
Yes.
So you see here we're in a clean copy of the GeoViewer. So I hit the 3 dots, I navigate, and it still remembered where the file was last time, to my detector geometry.root, and I click on upload. So that should update your left menu, but it shouldn't actually display anything yet. Then if you right click on default here, you go to draw and you select all. That is when the drawing should start. And then it will build and display the detector, and you can, do all the manipulation that you want to do with it.
Thank you. Right click. I did right click and then saw that. Okay, thank you.
No problem. It's a little counterintuitive, the steps to go through, as in, you have to know what to click on. You would think that just loading it should display it. And there's ways to make that happen, but then you can't use the menu bar. You have to actually, add it here to the URL, and then it will automatically load it. Anyway, that's how we do the display when we do it within the continuous integration. Any other questions?
May I make a question?
Of course.
I missed the discussion with Bill. So could you repeat how to include the IP6 a part of the detector? You showed how to make how to create a local copy of EPIC, but also could you show how to link these two things?
So what you do for this one, and let's just give this a shot. And I haven't looked at this in many months, so we'll have to discover this together. So let's go into IP6. So I did actually. let's clone IP6. So it's git clone github.com EIC IP6.git.
So are you sharing the screen or?
I am not. Thank you.
Could you? Yeah, thank you.
So here, can you see my screen?
Yes, thank you.
Okay. So I clone here IP6 instead of Epic. Then I go into IP6. And then I do the same CMake sequence. So we build into the build directory, this directory, and we create a new prefix within IP6 called install. There we go. We run the same compilation. And now let's look at what is inside the install. You see within install, there is a setup.sh again. And that sets the beamline information. So what you would do then is you would do source install setup.sh for IP6. And you would go into Epic and do source install setup.sh for Epic. It complains about IP6 not loaded because we're not using the old way of loading it. We're really manually build both and have both available now. And if you look at our environment, you can see that the beamline path is set here to our tutorial directory. And our beamline path is also set to the tutorial directory. So this will now pick up the plugins from the IP6 that are there. So it's exactly the same as for Epic, and you just do both. And then you don't need anything from the general detector, okay?
Okay, we'll try, thank you.
Yeah, and if you have any questions, I'm assuming that you have all access to the Mattermost. Please ask questions in the help desk of the Mattermost, and if there's multiple people that can help you, and also the answers to the questions are all available for for everyone to look at. Because typically, if one person has a question, there's a bunch of people that have the exact same question that are not asking it.
Okay, thank you.
Anything else? If not, please feel free to contact me or Wouter, ideally through help desk, or if you don't feel comfortable doing that, directly through Slack, to Mattermost, and we'd be happy to help you. Or there is help desk sessions that are announced on the Indico 3 times per week. Today, the help desk session will be at 2 p.m. Eastern time. Okay, then guys, I'll see probably a bunch of you at the Epic meeting, which will start soon, I think. And there is no tutorial directory in the container, Shyam. This is on my local machine. I just called, I think everyone else called their directory EIC. I called my directory tutorial. So this is really just an empty working directory that I cloned those 2 repositories to. Okay, if there's no other questions, then I wish everyone happy rest of your day. And yeah, see you at the general meeting. Stop recording.
Thank you, bye-bye.